Today we are going to see another class of differential equation that we call functional stochastic differential equation. Okay, the main difference of this from the other one is that here the coefficients like b and sigma does not only depend on the present state of the process but possibly the whole process, whole timeline. Okay, so b and sigma therefore are functionals. Okay, they are not functions of time and the space point but the time and the whole path. Okay, so now we first look at some definitions. Those are mostly recollections. Okay, and after that we are going to see the statement of the differential equation. We are not going to state any particular theorem about existence or uniqueness of solutions to those functional stochastic differential equations. However, we are going to talk about some properties. So if solution exists, then what are the things we can talk about there? Okay, so we start here. So we recall the definition of progressive measurability. Okay, so for each time small t positive, okay, let this sigma algebra gt is generated by all these maps S bar, which is taking the path to the vector point rd in the following manner, that S bar of the whole path, the path is here written as omega, S bar of omega is equal to omega of s. Okay, for any is in 0 to t. So here let us start again here. So t was a fixed time positive. For this fixed time t positive, we have a collection of time points s from 0 to t. Okay, this closed interval. For each and every s, we consider the map S bar. Which map? So S bar takes the whole path to a point in RD. Okay, and that is evaluation map, evaluation of the path at the point S. Okay, and hence this is a collection of maps which takes a whole path to a vector point, and we are talking about the smallest sigma algebra under which this collection of maps are measurable. So each and every member in this collection is measurable. The smallest sigma algebra containing due to that is called GT. Okay, so here we have not introduced any particular probability. Okay, since we have not put any particular probability measure on this set and did not start with any particular sigma algebra, although we know that the natural sigma algebra would come from the Borel sigma algebra on this, but we have not done that. So we do not also discuss about that whether GT is complete or not. Okay, so whether this measure on GT is complete or not. So we just have this filtration. Okay, and this gives me filtration, correct? Because now I would change my t increasing order, and then this collection would grow, and the sigma algebra would also become larger and larger, so I would get a filtration. Okay, that we call script G filtration. Okay, then function f from close 0 to infinity to and Cartesian product with the space of paths. This is space of path, correct? The space of all continuous maps from this non-negative interval to RD, correct? Because if I write down just C0 infinity, that means set of all continuous paths, okay, which is taking value in real number, but to the power d, that means I have Cartesian product, d number of Cartesian product of such things, so I would get path in d-dimensional space. So C0 infinity to RD. So f is a map, you assume, that which is taking a time value and the whole path, d-dimensional path, and giving me a scalar, real scalar. Okay, so this is a functional. Okay, we call this as a progressively measurable. Okay, if the following is true, that if this function, if you restrict in the interval 0 to t, so what does it mean? Because this function f, this functional is taking value t and also the whole path. But if I look at the domain only, not 0 to infinity but 0 to t, and on the second component I don't put any restriction. So this is the restriction of the whole function in a smaller domain, and there that function is defined now on 0 to t across the whole path space. This is the same as before, but here it is smaller. And then this with certain sigma algebra. Which sigma algebra should we choose? The natural one, the Borel sigma algebra on the interval 0 to t, and on this the sigma algebra what we have already introduced earlier. So for each and every, since I have fixed t, so I know for this t, gt, I have already defined. So I take Cartesian product of these two sigma algebras. I mean, this is not, Cartesian product to sigma algebra itself is not sigma algebra. So I mean that product sigma algebra, correct? So product sigma algebra coming from these two sigma algebras. So these two are BR. This is measurable for each and every t. Okay. So if my functional f is such that its restriction on 0 to t is measurable, okay, for all t, then we are going to say f is progressively measurable map. Okay, now here we introduce some notations. Now since we are going to state a stochastic differential equation which is functional in nature, so functional stochastic differential equation, so there, as I have mentioned earlier, the coefficients would look little different. They would not depend only on the present state value but the whole path. So here b is a function of time and function of the whole path, so continuous functions on 0 infinity to rd, and it is a real value. So I'm here presenting only one dimensional thing, okay, and sigma ij is 0 infinity to c 0 rd to r, be progressively measurable. So there is a typo, it should be r to the power d. So let me start from here. So there is a typo. So this bi is taking value time t and the whole path, d-dimensional path, and should give me a point in d-dimension rd, and sigma ij is taking a time point t and the whole path, and also should give me a proper matrix here. Okay, so that the matrix multiplication this with the Brownian motion gives me a d-dimensional point. However, here we did not fix what should be the dimension of the Brownian motion. If we choose that it is 1, then sigma is just a d-dimensional vector, so I can write d. Otherwise I should write down as a matrix, correct, d cross d prime. So here I have written that, okay, so here for every I, this is not a typo, is correct, because here I am not writing b, I am writing bi. So each and every components are scalar, are real valued. Sigma ij is also real valued. Okay, so these are progressively measurable, that is the assumptions on b and sigma. Now a weak solution, we are defining a weak solution to the following functional stochastic differential equation. So this looks like this, okay, that dxt is equal to b of t comma x dt plus sigma of t comma x dwt. Okay, so here earlier that sd looked like dxt is equal to b of t comma xt dt plus sigma of t comma xt dwt. But here b is function of the whole path. The whole path is present here, is not evaluated at time t. Sigma, also sigma depends on the whole path, and this FSD we call in short FSD because functional stochastic differential equation. Okay, so for this FSD we say that, okay, something is a weak solution. Okay, a weak solution of this FSD is a triplet, as we have also obtained a triplet for SD. So here also we are going to talk about this triplet. This triplet is this XW, omega FP and FT. So this is the Brownian motion and the process solution, and this is the probability space, this is the filtration. So this is filtered probability space and then this solution. Okay, so here the explanation of these symbols are given below. So omega fp is the probability space, and ft is a filtration of f having usual conditions. X is a continuous ft adapted RD valued process, and W is d prime dimensional Brownian motion adapted to ft, and probability that mod of b plus sigma ij square. Okay, so this integration, this would be a random variable, but this random variable is finite with probability 1 for all t. So basically this random variable is finite for all t that happens with probability 1 for each and every choice of I and j. Okay, so this is also quite similar to before this condition, and this condition also we have seen earlier. Only thing is that earlier we have written in a different manner. It was BISXS, but here no S subscript is missing. So probability that xt is matching with this is 1. So this says that choice of this W and this particular x, okay, if we put in this integral equation, then we would get equality for all t with probability 1. That is the definition of weak solution. Okay, so here we are not asserting any sufficient condition for existence or uniqueness of weak solution. We are just stating what do we mean by a weak solution of this particular FSDE. Now here we are going to look at some other definitions. So this is a generator, this is actually an operator we are going to introduce. This operator is introduced using the coefficients which appear in the functional stochastic differential equation. Okay, so let's just look at this operator, this a prime t. Okay, so that operator, if it is evaluated at a function u which is twice continuously differentiable, and this is a function of RD. Okay, it is not a functional, it's just a function. It's taking RD value and gives just one real number, and then y is a d-dimensional path. Okay, so this operator, when it is operated on this real valued function but evaluated on the whole path y, that is defined as half times this double summation, sum over I and sum over j, aij ty. So here y is the path, okay, and a is actually coming from sigma plus a. Since sigma depends on the whole path, so a also depends on the whole path, and it also depends on time. And then double derivative, the second order partial derivatives of u with respect to x and xj appear, and that thing is evaluated at yt. Here I cannot write y because u is just a function of vector. Okay, u is just a function of the present location of the path. So this double derivative, this second order partial derivative of function, that paths yt. Okay, so that is evaluated here, and then this summation bi ty, sum over all I. So here also b depends on the whole path y, and then del u del xi of y of t. Okay, so that is how we introduce this a prime operator, and this of course depends on t because here t appears. And then this operator, when we act on u, so we get a functional which depends on the whole path, so that path y is here appearing, and that appears on the right hand side also. Now we see a proposition which says that if this is FSD, what we have introduced in the earlier slide, has a weak solution, then how that solution is related to this operator. Okay, for any f1 and f2 which is continuous function of time and the space, and once continuous differentiable with time and twice continuous differentiable with respect to space. Okay, f1 and f2. So here u was just a function of space variable, correct? It's twice differentiable. But here we are taking f1 and f2, which are all function of time and space both. Okay. So when we take this f1 and f2, so using the weak solution, okay, so that means we are assuming that equation FSD has weak solution. So whenever it has weak solution, so that we write on xw this triplet, correct? We construct the following process. So 1 and 2, okay, so k I am writing in general, so k is equal to 1 or 2. So from f1, so like fk, so k is equal to 1 is f1. So from f1 we get m f1t. So this is a new process. This is defined, so m fkt is defined as fk of t comma xt minus fk of 0 comma x0 minus integration 0 to t del fk del s. So this is saying that, okay, with respect to the first variable partial derivative plus this a prime s fk, so that thing would be evaluated at sx ds. Remember that when a prime is acting on a scalar valued function, we get a functional. So after acting this, we get a function. So that is evaluated at sx. So x is the whole path. On the other hand, this del fk del s, the first order partial derivative of that would be just a function of time and space s and x, and then the meaning of this would be just del fk del s s xs. Okay, I mean it only take the value of xs. Okay. So this is, I mean, this way we are writing, but it is understood that here we have also a composition of evaluation map. So to be more precise, I should have written actually composition of evaluation of second component at time at the time point which is given the first component. Okay, so sxs. So this is a function of t because 0 to t integration. So as t changes, this changes. So this, and it involves the random process x. So this is a stochastic process. Here also this involves xt. So we get on the right hand side a stochastic process running in with a running variable t. And therefore mfkt is also a stochastic process we get. Okay, and then what we obtain or what we assert in this proposition, of course I am not giving the proof of this proposition, I am just going to state this proposition. It asserts that this new process mfk is a continuous local martingale. Okay, mfk is a continuous local martingale for each k is equal to 1 and 2. Furthermore, we can talk about the quadratic covariation of mf1 and mf2 is summation sum over all possible I and j or integration 0 to t, and then see that for the time variable these things do not appear here, only this thing appears. So here aij is there, so that appears here, aij is x del f1 del xi sxs del f del xj sxs. Okay, ds s is running from 0 to t. So that process would be the quadratic covariation of mf1 and mf2. In addition, if f is a continuous function with compact support, okay, so then and there exists a constant kt, k subscript t, for each t positive such that this sigma, okay, so sigma is here, so sigma actually gives rise to a. So sigma is bounded by kt for all small t between 0 to capital T, so uniformly bounded on this. Okay, so and y is of course the path, so d-dimensional path. Then this mf, okay, the way it is defined here would be square integrable continuous martingale. Okay, as we have discussed in the last lecture that for just the general SD, that this somehow captures the dynamics, therefore, because whatever the dynamics we get due to this xt, after the subtraction of this operator acting on f, we get a continuous, we just get a continuous local martingale, correct? So, and here for this specific case, when f is of compact support, etc., then actually indeed that local martingale is a martingale, so we get a square integrable martingale. Okay, so this is the proposition, which in a similar manner as we have done for standard classical SD, that this says that okay, this operator is associated with the SD, with the FSD, correct? So this is associated with the solution of the FSD in this manner. Okay, so in view of this, we say that this A prime T is associated with FSD. So now we look at a reverse statement. So the reverse statement is a continuous process W adapted to FT. So here what type of reverse statement we are looking at? We are looking at a very special case, much special than this. This is FSD, but we are looking at only SD case, that we are going to say that okay, the reverse thing is also true. That means here what we are saying, we are saying that okay, if I have a weak solution of the FSD, okay, and that we plug in here, and here sorry, that we plug in here, and and that FSD has some coefficients. From that coefficient I come up with this operator. If I do all these things, then I get a local martingale. But the reverse statement is that if I just take the coefficients of FSD and cook up this operator and ask for which process X, the resulting thing would be a local martingale no matter what if I choose. Okay, so that is the reverse statement. So this is the reverse statement for a very special case, only for Brownian motion. A continuous process W adapted to the filtration Ft is d-dimensional Brownian motion if and only if f of Wt minus f of W0 minus half integration 0 to t Laplacian f of Ws ds is in MC-log, continuous local martingale, okay, for every f in CRD. So imagine that we have one particular process W such that Laplacian we just have minus half Laplacian, so half Laplacian we have. So then this process f of Wt minus f of W0 minus half 0 to t Laplacian f of Ws ds as a function of t. So this process is a local martingale, continuous local martingale, no matter what f I choose. Okay, so here I have there is a typo, it should be C2, twice continuous differentiable. No matter what twice continuous differentiable f we choose, we would always get this as a martingale, continuous local martingale. Okay, so such process, call that is a solution to the martingale problem associated to half Laplacian. Okay, so if W is a Brownian motion, of course this becomes a continuous local martingale that we have seen, but the reverse thing is also true, because a continuous process, this is a d-dimensional Brownian motion if and only if. That means if this becomes a martingale, continuous local martingale, then W is a Brownian motion. Okay, so this is just if and only if condition. Okay, so in this case, what we say that W is the solution to the martingale problem associated to half Laplacian. So what is a martingale problem? A martingale problem is basically if I have an operator here and if I fix also the class of paths, so path space. And then on the path space, we look at the coordinate process. So W would be just the coordinate process, and we don't know that what is the measure there, but we are looking for the measure on the path space such that the resulting this process in T, okay, becomes a local continuous local martingale for each and every choice of F. Okay, and if that problem has a solution, the solution would be what? The solution would be a measure on the path space. Then that measure is called the solution of the martingale problem. Here we actually say it in a very colloquial language that okay, W is a solution of the martingale problem. What does it mean? That the law of Brownian motion is, which is actually a probability measure on the path space, so which also we call as Wiener measure. So that is the solution of the martingale problem as to do with half and Laplacian. So this is, I mean, we are not heading to go into more details about martingale problem. So in general, existence of solution to a martingale problem is equivalent to the existence of a weak solution. Okay, you can see the chapter 5.4, so chapter 5 section 4 of characterization sheet for more details. Okay, so that gives more details about this treatment, not only for only Brownian motion, but for the SD and FSD also. Okay, so now I go to the next part.